All right, continuing. Let's look at the derivative for any other log with any base. The log of x with base a. All right, now that we know the derivative for the natural log of x, we can use that to our advantage. We're going to start with the change of base formula, and we're really just thinking of it. We're beginning with the true statement. You may recall that the log of x with base a could be rewritten using natural logs, the natural log of x divided by the natural log of a, no matter what the base is. Okay, so we've got this true statement. What are we going to do? Well, of course, we're going to take the derivative of both sides. And now we can see, oh, okay, this is what we want, right? The derivative of any logarithm. We just got to figure out what this is, and we know how to do natural log x, so this will go well. Okay, so we've got the derivative of the natural log of x over the natural log of a. One thing to point out: the natural log of a is a constant, because for any given example, right, you'll have a number there for a. So this is the natural log of a number, and the natural log of a number is just another number, right? So we've got that constant in the denominator. So we're going to think of this like a constant multiple. We're going to separate it from the natural log of x, like this. We're going to pull it out. Now, it needs to be 1 over the natural log of a times the natural log of x. So this whole thing is a constant multiple. And there's our function. So with that constant multiple rule, I'm going to say, oh, all right, this is just going to carry along. And it's going to multiply with the derivative for natural log of x, which is 1 over x. And so, clean it up a little bit, put those together, multiply the fractions, and you usually see the x in front. 1 over x natural log of a is your derivative here. Okay, that's interesting. Let's let that sink in for the next couple of minutes with some examples. We'll start off real simple. Just y equals the log of x with base 3. Okay, so what's the derivative here? Well, we've got the rule. We know the base, so y prime is equal to, well, 1 over x times the natural log of our base. 1 over x, natural log of 3. Turns out the derivative for any type of log is going to have the natural log involved, the natural log of the base. Just like that. All right, let's do a slightly more difficult one. One that will involve the chain rule, always a good idea. Okay, and I've got a little something else over here. We'll just cover that up. How about f of x equals the log of x squared plus 1 with base 6? Okay, so here's where I will uncover this. Just like in the previous example, if it was simply the log of x with base 6, then we'd say 1 over x natural log 6, right? But now we have something more than just an x there. We've got x squared plus 1. So the rule is for the chain rule, whatever appears here is going to appear here as well. And that would be the derivative of the log. We'll still need to multiply by the derivative of what's inside there. But to get that derivative of log base 6, we're just going to follow this same pattern, but inside this is what's inside the log in the first place. So here's the whole thing. Let's talk through it. Here's the derivative of the outside, the log base 6. 1 over x squared plus 1, natural log 6. Again, whatever's inside there is just going to go in that position. Then we multiply the whole thing by the derivative of x squared plus 1, which, of course, 2x. There it is, and, well, we might as well write it, clean it up just a bit, put that 2x, multiply it up on top. Here's our derivative right there. Now, it's no coincidence that we save the derivatives for logs until after we learn the product rule and the chain rule, quotient rule, even implicit differentiation. And it's not that we didn't have to. We could have discovered, derivatives like this way back, even right after we learned e to the x. We then could have immediately learned the derivative for natural log x and then other logs, right then. We didn't have to wait until after chain rule. But we do wait until after chain rule. It's wise to do that just because the derivatives of logs are strange. The rule seems kind of weird. It takes a little while. It takes some practice before it sticks, right? Just kind of, I didn't put this in my main notes, but I think it's a good point to make. If you're taking the derivative of a polynomial, right? A derivative of a polynomial is always another polynomial. Just the powers change and the coefficients, right? The derivative of e to the x equals e to the x, right? That one doesn't change at all. The derivative of a trig function is just another trig function. All right, the derivative of a quotient is another quotient, right? So we kind of there's this pattern that things don't really change that much. But then all of a sudden when we learn the derivative for the natural log of x, the result doesn't involve natural log. It's 1 over x. And that just that seems unnatural, right? That this would not involve a natural log in any way, but it doesn't. So, and then then we just learned this, and this is even more unnatural, right? Not only does it not have a log base a, it's got a natural log of a, but it's just, but then it's a fraction. It's like, what? That just catches you off guard. So it's something to get used to. It's something to recognize. Okay, yeah, everything else, like what's different about this? Why is this giving me a hard time? A typical student might say, well, because a polynomial derivative is a polynomial. A trig goes to just something else in trig, but this just changes completely in that. Okay. And that makes the chain rule difficult. And okay, anyway, there was our answer here. Hey, let's kind of reflect on this. I've got this note before we go any further. What if you thought about the natural log of x as having the base e, right? So we pointed that out earlier. Natural log x is the log of x with base e. What if we used, this formula here with e as the base? Would it still all fit? Would it still work out to be what we know it is? It would. Check it out. Y prime would be 1 over x times the natural log of e. Right? Following that pattern. But what's the natural log of e? The natural log of e, and grab a calculator. If you don't remember, if you're having trouble, the natural log of e equals 1. So it is just 1 over x, even if we follow that other pattern, that other rule. You could really say that natural log is a special case of the more general rule, where that just happens to be 1. All right. All right, we're about to come full circle. What is the derivative of any other exponential, a to the x? Okay. Well, we're going to use what we just learned. All right. We're going to start with this true statement. The log of a to the x with base a equals x. You may recall that the bases here would cancel out. Okay. So, of course, what are we going to do? Take the derivative of both sides. The derivative with respect to x, the log of a to the x with base a equals the derivative with respect to x of x. And what's that going to do for us? Okay, well, here we have a chain rule. Again, this is the inside. Okay, what's inside the parentheses? So what's the derivative of the outside? Well, it's 1 over this times the natural log of the base. But then we need to multiply by the derivative of that inside function. And of course, that's the question we're after in the first place. So we're just going to leave it in this way. So derivative of the outside times derivative of the inside, and this equals 1 over here as well, similar to before. And so if you wanted to know what this derivative equals, well, what do you got to do? Just multiply this denominator over to the other side. And here it is. The derivative of any exponential, a to the x equals a to the x times the natural log of a. Now this one takes a similar theme as e to the x, right? It does repeat itself, but that's not all. We then need to multiply by the natural log of a, and that's kind of similar to that, the rule we just learned with any other log. At least there's some similarities there, right? Similar to this rule. Okay, a couple of quick examples. Let's just do one real simple. F of x equals a to the x. 8 to the x. I might have misspoke there. 8 to the x. Well, if we follow the pattern, what's f prime? It repeats and then multiply by the natural log of our base. 8 to the x times the natural log of 8. There it is. Okay, let's do one that's a little bit more difficult. Gonna use a chain rule. Good practice. G of x equals 2 raised to the x cubed plus 3x squared plus x plus 1. We're raising 2 to this polynomial. That's all in the exponent. Just to be clear. And at this point, sometimes students think, when would this function ever come up? Seriously? Hey, you got to be prepared for anything. You never know. Okay, so we have our constant is here. Our variable is there. So we know that's an exponential. The variable is in the exponent. We've got a chain rule. This whole thing is the inside. And the 2 is the outside. So how's this going to work? Okay, so maybe I should slide back here. What's the derivative of the outside? Well, that's this whole thing, okay? So we copy it, and then we multiply by the natural log of our base, which is 2. Okay, so let's go for it. Turns out this is the whole thing. Let's just show you everything. The derivative of the outside. We copy it, and then multiply by the derivative, then multiply by natural log 2. Then for the chain rule, we got to multiply by the derivative of our polynomial. So we need some parentheses. 3x squared plus 6x plus 1. There's the derivative of the inside. And that is ugly, honestly. But what are you gonna do? That's what it is. Okay, let's stop this video here. There is some more we need to say coming up.